So this small group now has the responsibility of this heritage that we will bring further. Good. Water footprint of sugar and ethanol. What am I going to talk about? In this presentation, I'll show things about the availability and the role of fresh water, because we're not talking about water, but we're talking about fresh water. I'll explain this water footprint concept, and this concept can be applied also for sugar and ethanol. Good. What's the problem? Well, some years ago, we did an assessment for the Coca-Cola company. And as I mentioned before, in the Netherlands, we developed this so-termed water footprint concept. And we organized ourselves in a so-termed water footprint network. It's still located in Enschede at the University of Twente. And when this was founded, one of the first members became the Coca-Cola company. So then they also came to us because they were very interested in their corporate responsibility to make an assessment for their Coca-Cola. The idea was that we would have the ingredients of the cola. Of course, we didn't get that because it's a secret. But we made the assessment, and for what we see here, if it's working. Try to use the pointer. It's not really working. For a small bottle of Coke, 250 milliliters, well, of course you need so much water, but most of the water is needed to produce the sugar. So it's related to the sugar. It's not needed in the plant itself when you produce your cola, but it's needed in the supply chain. So what we need to do is go back in the supply chain. This is just an example of how our water footprint works. So around 10, 15 years ago, as I mentioned, we established this network. Companies became very interested in their water use because it was part of their corporate responsibility. So they not only looked at their carbon footprint anymore or land footprint, but they included water. And what we discovered is that many businesses did not really know where the ingredients in their supply chain came from. For example, we also did assessments for Unilever. They had no idea. So if you want to do an assessment, and in general we see that the operational water footprints are small compared to the supply chains. So if you really want to do something, you have to look at the supply chain. Of course, the operational water footprint needs to be fine, so no pollution control. But then going back in the chain is far more important. This was an introduction to what I'm going to say. First, the availability and role of water. So it's about fresh water. It's not about salt water or brackish water, because the availability of fresh water is a limitation. But we need it for just everything. We need it for households to drink. I was surprised by all the bottles that I emptied that after a few days in my room. I had a huge pile of bottles, bottles just everywhere. Of course, you need to irrigate your crops, but there are also other uses and other large consumers of fresh water, like electricity generation in power plants. At the moment we have a huge project together with CGR that we look at the water for electricity in Africa, looking at all the power generation in Africa. But then about water. I'm taking a step back, so I don't look at the companies anymore. I look at the global water cycle. Very often my students say, okay, why would we be concerned about the availability of water? Because the volume of water on our planet Earth is a constant one. So, yeah. But then it's about where is my water and when is this water available? Of course, you see here the hydrological cycle, very large simplification of what happens. Your water evaporates, it forms clouds, it starts raining, and it flows off to the sea again. Simplification. But then, when we start thinking about climate change, when I look at my country, what's happening there, or when I left to India, it was cold. And normally, when I was a kid, it was cold and we could go skating on the water. But now it's only a few days in a year. We had much precipitation in autumn. And the crop fields were so wet that the sugar beets could not be harvested anymore because the farmers could not go into the fields. So this is an example that in my country we see that the changes are going so fast that we can see it. It's not a gradual change anymore, because if things go gradually, you don't observe it quite well. But these things are now happening in a few years. We see fires of the forest, so something is changing in this hydrological cycle, which has huge consequences also for the availability of fresh water. Most of the water on our planet is salt water, so we can't use it. We need fresh water. So only 3% of the water available on this globe is fresh. But then again, we cannot use it all because we don't have access to all the water, because part is stored in ice. But then of course also climate change is going to do something about that one. We have huge groundwater stocks. We can pump it up to use it for agriculture. But only a minor part of our total fresh water on this globe is surface water, where we have access to. When we look at the water withdrawal per sector in the last 120 years, then we see an enormous increase in the water use. And of course we know these types of graphs from CO2 emissions and energy use, but this also holds for water. It goes up quite steeply. And what we also see globally is that, it's working. Most of the water is withdrawn for agriculture globally. A minor part is domestic water, and about 1/5 is used for industrial purposes. So some for power generation, primary energy production, and other industries. Now, if we specify a bit more, if we zoom in a bit more, in the same period, we see that it's especially agriculture. And what I show here is that there's a difference between the actual withdrawal and the consumption. when we withdraw water, we don't consume everything. Part returns to where it came from. So we are interested, and also from a water footprint perspective, we are interested in the consumption. So the water that is actually lost and that's not available for use anymore. So what we then see is that there's a huge difference between the consumption and the withdrawal in agriculture, and this is by far the largest. Domestic use, the difference is far larger, so we withdraw. But then when you treat the wastewater, it goes back, it returns to where it came from, so it's not actually used. And in industry you have the same. For example, if you use water to cool your power plant, you take it from a river, or you take it, well, sometimes even from groundwater, and then it goes back with a higher temperature. Yeah? Further zooming in, where is the water used? And then what we see is that here, Asia. Asia is the largest consumer, and this of course is not strange, because we have the largest world populations over here: India, Pakistan, Asia, Southeast Asia. Africa is quite small. South America, they can use rainwater, so they don't need to irrigate so much, but also the United States is large. In central USA, they pump up the water from aquifers. For the sectors, Asia, the withdrawals are mainly dominated by agriculture, 81%. So if I relate this to one of my first slides showing the operational water footprints in a company and the supply chain, if we want to do something, if we want to save water, we really need to go to the first stage, so agriculture. Europe, it's small. In the north of Europe, you don't need to irrigate so much. It's mainly in southern Europe. Okay, then the water footprint. If we want to know something about water withdrawal, water consumption, we need to make assessments. We need to make calculations to find differences, and to find differences among countries, among provinces in countries, among crops. Where is the water used? Without this information, I cannot become more efficient. So the water footprint is part of what we term the footprint family. The first footprint was developed by Wackernagel and IREES in the last century. This was the ecological footprint. They came from Canada. And what they did is that they introduced a way to calculate land use, and also land that was needed to take up carbon again, that you could relate to human consumption. So what they did is that you can relate human consumption patterns to land use. This was, well, an example for Professor Hoekstra, who developed this water footprint concept, which is basically the same. So you relate consumption with water. The CO2 footprint came later. So let's focus on this water footprint concept. Yeah. What we can do with this is that we make an assessment, basically first, how much water do I need for a specific item. But what it also does is that you can relate the origin of your item to your consumption, because as we sit here, I think we all wear something that's made of cotton. No? Now, there are some large cotton regions. I think also cotton is produced here in Asia, but this is probably you have seen this picture. This is the Aral Sea. The rivers that feed this Aral Sea are completely pond dry because they use the fresh water for the irrigation of the cotton fields. So if we consume cotton, we are also responsible for what's happening here. And in this way, you can relate your consumption to the production places and see how responsible we are. Okay, so when we make a water footprint assessment, we go to 4 phases. You first set your scope and goal. What are we going to do this assessment for? What is my purpose? What do I want to know? Then phase 2 is the actual footprint accounting. So I start calculating. So I need to make an assessment of how much, well, if we talk about agriculture, how much water do I need to grow a specific crop? But then comes the so what question. What is the aim of my assessment? So I want to make my consumption more sustainable, so I need to do some way or another a sustainability assessment. And then the final phase is the water footprint response formulation. Now you can make this assessment using this water footprint concept, but you can also do a life cycle assessment. Yeah? LCA is also a very well developed tool to make assessment, to look at sustainability of production. Initially, LCA looked very much at pollution, and later they also introduced water in their assessments. And they do the sustainability assessment a bit differently than we do. There is now an ongoing, discussion between the two communities to come to a general concept that we integrate LCA and water footprint assessment. We are working on a common paper right now. So what we need to know then, if we want to make this assessment, we need to know what this chain looks like. So we need to know if I have an ingredient for a specific product, where is it coming from? I need to know where my water is coming from. So I need to know also the supply chain of my water. If I have a crop field, then I need to know where my water is coming from, because what we quite often see is that you have huge losses in your supply chain. For example, a PhD candidate of mine, he looked at the water supply in the Indus Basin in Pakistan, finding enormous losses. And this has to do with poor management of the water supply. Okay, then you go to the farmer stage. You go to the food processing stage. You go to the retailer, and finally your product ends up at the consumer. Then we define 3 types of water. We look at green water footprints, which is basically precipitation, mainly rainwater. We look at blue water footprints, so it's the water that you withdraw from groundwater or from surface water. And then there's a final one, a gray water footprint, and that is a theoretical footprint that expresses how polluted your water is. So we define it as the water that is needed to assimilate the pollutants. And then of course there are different standards in different countries about what are acceptable water quality standards. So it also depends on where you are. Now, thinking back at our company and the supply chain, we identify a direct water footprint, so the water that is used at the place where, well, it's actually used, and the indirect one that's in the chain. And then you can see the three colors, so green, blue, and gray. Green and blue are related to the actual consumption of your water, so how much water do I need to produce my product? And then the gray one is related to the water pollution. Now, when we look at the statistics, because we need water source data sources to do this, when you look at the statistics of, for example, FAO, Aquastat in FAO, you see that they report mainly the withdrawal data and not the consumption data. So these are the traditional statistics. We developed a huge database that is available on the website of the water footprint, showing all these water footprints, so the separate colors per crop, per country, per province. So if you want to do an assessment, say, about the consumption pattern in a country, you can use those numbers to make your assessment. Okay, so then a definition. The water footprint of a product is the volume of fresh water to use to produce the product, summed over the various steps of your supply chain. And therefore, it's different than CO2 emissions, because here it's more complicated because you have a temporal and a spatial dimension. It matters when and where you use your water, and that creates differences. If we want to assess the water footprint of a product, we use the crop water use, so cubic meters per hectare, and we expressed it in units of yields. So this basically means that the higher your yield on a unit of land, the smaller your water footprint. This is for a crop. We could also make an assessment for the water footprint of an animal, but then you need to know how much feed is going into your animal, and you have to sum it up over the lifetime of an animal. And when we have products with more end products, you have to distribute your initial water footprint, you have to allocate it over the derived products. Then I was talking about the sustainability assessment. So in some way you have to make an assessment, how sustainable is my water use. So what we then do is that we look at the blue water footprint, we do that per country. We know the water availability, and then you can compare the water scarcity. Water availability is expressed in the water footprint concept as we look at environmental flow requirements. So that basically means that you cannot take out all the water from the environment, because then you would really harm your environment. So we assume that around 80% needs to be available. Yeah, so you can take out roughly 20% without too much harm to your environment. But what we then see happening is an enormous blue water scarcity, then especially in Asia, North of Africa, but also in Europe this occurs, depending on the months in the year. So here we see an overview of the annual average monthly blue water scarcity, and then India and Pakistan are popping up, parts of Australia, but also in the United States, southern Spain. So developing this concept, and then you can use it to start making your calculations. And we have all these numbers. We did that for a huge amount of consumer products, so varying from all the food products, but also for cotton and shoes and power. Now, in general, and you could expect this already, products that are based on crops, so sugar, they are low in the pyramid, so they relatively need less water than the other products, for example meat, because then I need all the feed ingredients that go into the animal, and then you get really huge water footprints. Now, showing all these numbers also made that there's, well, at least in my country, there are advices to eat less meat, because the pressure on our freshwater resources becomes too large. We also made these assessments for sugar, and then you see the enormous amounts of water that you need for 1 kg of refined sugar, but this is a global average, and it varies a lot among countries. As I mentioned before, my group made this huge database with water footprints of all the crops and crop-derived products. And then we decided, okay, now we have it for crops, we can also do this exercise for bioenergy. So we were the first to make an assessment of the water footprint of bioenergy, so for ethanol and for biodiesel, because initially the biomass is the same, whether or not you make a food out of it or if you make a fuel out of it. So you can use your biomass to generate electricity and heat directly. So you can use trova, or you can use wood and burn it. For example, here in India, they use a lot of wood for cooking. You can also use it to make a product. For example, you have sugar cane and you produce your sugar, then you have a residue left. Then again, you can use that residue for something. You can also make ethanol or biodiesel out of it. So depending on the purpose, what you want to do with this. Now this is a figure from our first publication that we made. What we see here is that from a water perspective, it's more efficient to produce bioethanol than biodiesel. So that's my first result. We see here a distinction between blue water and green water. Now, if you remember, then the green water footprint was the precipitation. So basically, this is for free. This is what's falling from the air. So this is free, and this is my blue water or my irrigation water. So I see that there's a huge difference between the crops. Yeah, some crops need far more irrigation than others. The sugar beet is very efficient, The sugar cane, well, it's also fine, but it's less efficient than the sugar beet. We could also do this for other crops that have a carbohydrate content. So for potato, for maize, cassava, barley, rice, paddy rice, and wheat. And here we find the oil crops. Now maybe this jatropha was an interesting one. Yeah. I did not know at that time about jatropha, but I wanted to include it in my analysis. But then I got a lot of comments about this because at that time, we're talking about 15 years ago or so, there were huge interest from business to go into jatropha for the biodiesel. We also made an assessment for sugar and for bioethanol globally. This is one of the figures from that publication. Here you see the sugarcane areas. Here the Indus Basin and the Ganges Basin, and here this is where we are now. And you can then relate it to the water availability and water scarcity in this area. Water footprints of sugar cane. I just showed the global average. What we see here is the difference between countries. And then you can see the locations or maybe the agricultural practices that are less favorable. For example, here we see Egypt that has a huge use of irrigation water. We here see Cuba. Cuba has more precipitation, it doesn't use so much irrigation, but the overall water footprint is far larger, and probably this has to do with low yields. Then I'm showing another example of how we can decrease our water footprints. This was done by one of my PhD candidates who is now working for the Ministry of Agriculture in Pakistan. What we wanted to do, we knew exactly where the crops are grown, and we knew the combinations of crops, so the cropping pattern. So we knew where they were located, and then we wanted to optimize this. We did the same exercise for Iran, and we could decrease the water use. So what we see here is that when you start moving your crops, and we did this for water and we did this for energy use that is needed to pump up your water, we try to optimize both. So first the water by moving the crops, then you can decrease by about 10 to 15%, and then the energy footprints, and you can also see that that goes down. So what we see is here the relative gross blue water footprints of the sugar cane. So it's more efficient in the south than in the north, and for energy this is the same. And then we start optimizing, so moving the crops. Basically the sugar cane goes to the south where it's more efficient. We did a similar exercise for transport fuels, looking at the water footprints, and what we then see, because in the European Union there's a policy to blend petrol with ethanol, but there is also a tendency to use more electrical cars. So we express this in terms of water, and what you then see is that, this is a logarithmic scale, so the differences are used. So that especially when you start using your ethanol, your footprints are sky high. hydrogen is a bit better, and for electricity it depends very much on the source of your power. If you use the mix that we have now with natural gas and coal, then it's not so good in terms of water. And something about ongoing research, because what I showed was present results. We have a new PhD candidate in our group, and she is going to look at the future water availability for food and energy development in Pakistan. Because what we see is that what we have is presently, maybe you heard of this energy drought, that when there's not enough wind and not enough sun, we cannot generate electricity, but something similar could happen to snow droughts. What we see is that at present, snow is melting, the glaciers are shrinking, and this could have an enormous impact in this area. And this PhD candidate is going to model the future water availability that is generated in this area. So this is the Hindu Kush Himalaya area. She's going to use about 40 models to see what will happen in the future. But these mountains, they are the source of very important rivers. In China, here in Southeast Asia, we have the Mekong, yes. We have the Ganges River and we have the Indus River, and this might very much affect agriculture and possibilities for agriculture in these areas. So this is ongoing work. I think I got a note here that there's no time for questions anymore. Then you can